ॐ सहनाववतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः।
So, we are talking about CMOS technology. CMOS technology, which is one of the most important technologies in today's VLSI. Now, from the point of view of technology, in a CMOS, we can realize both a P channel and N channel MOSFET in 3 different ways. That is, one is you start out with an N-type substrate and form a P-well there, which is a P-well technology, and because you are starting out with the N-type substrate, essentially it is compatible with the PMOS fabrication process flow. So, N-well technology, which is P-well technology, which is compatible to the PMOS process flow, and then similarly we can start with a P-type substrate analogous to an NMOS process flow, and in that P-type substrate we can create an N-well. So, we can have in CMOS technology either a P-well or an N-well, or better still, we can start with a very low doped substrate material, nearly intrinsic, and we can have both the wells, which is called the twin well or twin tub technology. Twin well or twin tub. These are the 3 different ways in which a CMOS can be realized. Okay. Now, in this twin well technology, again we can have either a true twin well, that is, in which case you really start out with a nearly intrinsic substrate and you dope both a P well and an N well. The other possibility is to have a secondary P or N well. The secondary P or N well, in this twin well is essentially an extension of either this P well or this N well technology. Okay. In this secondary case, again essentially you start either with an N-type substrate, okay, and then essentially you create in that N-type substrate, you essentially create a P well only, okay, but you do a deep substrate implantation to prevent the punch through in the N-type substrate itself. So, what is happening in the secondary, let us say if it is secondary P well, you are starting with an N-type substrate, you are actually creating a P well here. Okay. So, see basically it is an extension of this P well only. Only thing what you are doing is in this N-type substrate you are having a deep somewhere deeper inside you have an N to prevent punch through. Okay. So, this is the secondary P well. In the same manner, you can also have a secondary N well, in which case you basically have an N well, but in the P type substrate also you carry out a deep implantation to prevent punch through. Okay. Now, as far as the CMOS technology is concerned, these two are the most important techniques today. Okay. Previously, because NMOS was the dominating device, the most widely used MOSFET, we used Nwell technology, which was compatible with the NMOS process flow. And now, as CMOS itself has become the dominating device in VLSI, now we use Twinwell or Twinwell technology. Okay. So, let us first discuss the Nwell technology, how exactly the well is created, and then we will go over to the Twinwell technology. Now, in the Nwell technology, obviously, you start with a P type substrate, right. Remember, with better understanding of the oxide charges and the interface states, now we know that 100 substrate has at least one order of magnitude lower interface states. So, for MOS technology, universally we use 100 substrate. In contrast, the first metal gate P MOSFET which was fabricated, it was fabricated on 111 substrate. That was because it is a very old technology. In those days, 111 was still the by far the cheapest substrate, right. People did not quite understand the relation between the substrate orientation and the interface state density. But then as it became clear, now for any surface devices, MOSFET is a surface device. In contrast, bipolar junction transistor is a bulk device, right. So, for MOSFETs you always use 100 substrate, right. Okay. So, in the conventional Nwell architecture, you start out with a P type substrate, 100 P type substrate. Right. Now, your first mask is going to be the Nwell mask, that is, I must dope certain region in this P type substrate as the Nwell. And how do I do that? I do that by a low cost technique. That is, I protect certain region of the P type substrate using an oxide nitride mask. This is nitride sitting on top of the pad oxide. You can have finer techniques here like sidewall masking and all that, don't let us bother about that. Essentially what you do is you are planning to carry out a low cost technique. You are going to protect certain region in this with an oxide nitride mask, and the rest of the region you are going to have a phosphorus implant. Okay. So, you see this implantation can be a blanket implantation. Certain regions are protected by this silicon nitride, silicon dioxide mask. Okay. So, you can just with this mask on, you can just put it on for a phosphorus implantation, right. And once you have the phosphorus implantation, you have certain regions doped N type. Okay. Now, in the next step, you carry out the drive in, okay, in an oxidizing ambient. You see, you want to have an OL, you want to have a deep NP junction, right. So, you carry out the drive in an oxidizing ambient. So, what will happen? oxide will form over the regions which are not protected by the nitride and oxide mask. So, what I will have is, I will have the oxide grown like this, and in the process this whole thing will be driven deeper like this. So, this is your N region, this is the nitride and this is the oxide. Okay. Now, I want to strip off the nitride as well as the thick oxide that is grown on top of the well. I want to strip off both this oxide as well as this nitride and oxide. So, what do I have if I strip it off? Right? I create a step in the semiconductor. What is the purpose of this step? This step actually signifies the position of the Nwell. So, now you have marked the two places. This is the region where you are going to form your N MOSFET, this is the region where you are going to form your P MOSFET, okay, and this step demarcates the two regions, right. Next is of course very simple. After you have achieved this, in these two regions now you have to have the field oxide and the area for the active transistor. Okay. So, again you see you have to carry out oxide nitride combination and pattern it. And then carry out low cost. Okay. But before carrying out low cost, what you can do is, you can do the boron implantation for the channel stop, right. Remember we mentioned this yesterday, that underneath the field oxide the substrate doping must be raised, so that the parasitic MOSFET does not get inadvertently turned on. Okay. So, after you have protected certain regions, you may or may not want to etch the silicon. If you want a recessed oxide, you will etch silicon to the required depth. If you do not want a recessed oxide, you do not have to etch, okay. But you do a boron implantation. And of course, when you are doing this boron implantation, you have to prevent this implantation from going into the Nwell. So, this region must be masked with photoresist. You are using ion implantation, so no problem, photoresist can be used as a mask, and there also you see this indentation will come in very useful to align the photoresist mask onto the Nwell. Okay. So, now you have done the boron implantation, which is the channel stop implantation for the NMOS, and in the next step you grow the thick oxide. So, now underneath this you have boron implantation. Maybe I should just show it with dots. And now I can remove this silicon nitride oxide mask. So, you see you have your two active transistor areas defined, right. Rest is all protected by thick field oxide. You have your Nwell. This is the region where your PMOS is going to be spaced. This is the region where your NMOS is going to be spaced. You have done the channel stop implantation to stop the parasitic MOSFET from getting inadvertently turned on. Next, you can just follow it up with gate oxidation, gate polysilicon deposition, patterning and source and drain diffusion. Right. So, what were the steps? The first step was to have a nitride oxide mask for the Nwell. First, you have a nitride oxide mask to demarcate the regions where your Nwell is going to be placed. Okay. Next step, you do a phosphorus implantation to form this Nwell. Then you carry out the drive in an oxidizing ambient, so that the Nwell is driven deeper, and at the same time you have a thick oxide forming on the Nwell. After this, you do the stripping of nitride as well as oxide. Because there was a thick oxide formed on top of the well, you have a step in the semiconductor surface which helps you to identify the Nwell regions. Okay. Now, in the next step, you again do a nitride oxide mask step, but this time this is in order to define the active transistor regions. And with these masks in place, you carry out the field oxidation, but prior to that you do a channel stop implantation. Now, you do the field oxidation. So, you see apart from the active transistor region, the rest of the surface is protected by thick field oxide. Underneath the thick field oxide in the NMOS region, you have the channel stop implantation, and you have your both your PULs and NWell, I mean both your PMOS regions and NMOS regions clearly defined. So, now you can follow it up with gate oxidation, patterning, source and drain diffusion. Okay. So, this is the conventional Nwell technology, which is compatible with the NMOS technique. Okay. Now, in the twin tap technology, of course, will form actually two wells. In this case, we have formed only one well, that is the Nwell. In the twin tap technology, we are going to actually form two wells. Okay. So, you start with a very low doped P-type substrate, very low doped P-type substrate. Okay. So, let me start with a very low doped P-type substrate. At the beginning, again you have a locus, that is, you first of all protect certain regions using the pad oxide and the silicon nitride. Okay. Remember, in this case I only had one mask, I only had to protect the N MOSFET region. Now, I have two masks, because I am going to have two wells, I must protect both the regions. Okay. After this, you can do a boron implantation. actually this is a blanket implantation, that is I do not use a mask. Okay. With this silicon nitride, silicon oxide in place, I carry out a blanket boron implantation. It is diffused P, implanted P all over. Okay. Now, you have the Nwell mask and you implant it. So, what do? We just use photoresist as the mask. And the rest of the region we do phosphorus implantation. Maybe it is not so critical, so it can actually come up to this. If we do a phosphorus implantation, this implantation dose is much higher than the previous boron implantation. So, what you have essentially is you have the Nwell. Okay. After this Nwell is formed, you do a boron low energy implantation, low energy boron implantation. So, what you have is you just protect this region now. This photoresist here, do a low energy boron implantation. Because you are doing it at low energy, this mask will mask the boron implantation. You will have just boron here and boron here. So, essentially what you are doing now is the channel stop implantation for the N channel MOSFET. So, you see this is actually the example of the secondary Twinwell, secondary Twinwell. Okay, I told you that in Twinwell I can either have a true Twinwell or I can have a secondary well. This is essentially a secondary well, in which case you see I have actually formed the Nwell. I have started out with a p-type substrate. I have actually formed the Nwell, analogous to in this particular case, but there is one additional step involved in this. What is this one additional implant? That additional implant is the first boron implant which I have done, so that I have a buried deep B implant. Okay. This is done in order to prevent the subsurface punch through. So, essentially this technology is analogous to the Nwell technology. The only difference is in this additional boron implantation, which is helping to prevent subsurface punch through. So, this is an example of the secondary Nwell twin tub. This is not a true Twinwell technology. This is a secondary Nwell technology. Okay. Now, let us come to a true Nwell technology, true Twinwell technology. true Twinwell technology, you actually can start with either p-type or n-type substrate. The only requirement is that your substrate must be very low doped. It should be near intrinsic. So, I do not really put a restriction on what should be the type of the substrate. I can have either very lightly p-type substrate or very lightly n-type substrate. Okay. Only thing I do is I protect certain region in this by using an oxide nitride mask, okay. And then I do first, in this particular case I have taken a phosphorus implantation. So that you have your Nwell. Okay. Now you see, now you carry out an oxidation over the Nwell. I mean you subject the entire substrate to an oxidation process. The oxide is going to be formed only over the Nwell because the rest of the portions are protected by the oxide nitride mask, right. And while you are doing this oxidation, this Nwell would also be driven deeper. So, what would you have at the end of that oxidation process is something like this. You will have an oxide and underneath you will have the Nwell. Okay. So, you have already formed your Nwell. Next step, what do you have to do? You have to form your P-well. In order to do that, first step you strip off the nitride. Okay. Now, I carry out a boron implantation. I do a P-well implantation. Now, the interesting thing is usually in these kind of Twinwell technologies, you know, we use mask for one well. Already I have used that mask for the Nwell. Okay. I protected certain regions using the oxide nitride mask, and then I have done the phosphorus implantation. Now, you see I have grown a thick oxide on top of the Nwell, okay, while on top of the rest of the portion there is only a very thin oxide. So, the implantation energy is such that it can penetrate this thin oxide, but it cannot penetrate this thick oxide, right. So, now when I want to carry out the P-well implantation, I do not have to bother about any mask. I can do a blanket implantation. The whole point is like this: as we are reducing the device dimensions, it becomes more and more critical if we have a lot of alignment, lot of mask alignment to do. Okay, the smaller the device dimensions are, the more difficult it is to align. So, we always want to go for self-aligned technology, right, where one region is automatically aligned to the other. So, this is what we are achieving here. You see, we first defined a mask pattern. Using that mask, we have our Nwell implanted, okay, and driven in an oxidizing ambient, so that there is a thick oxide formed on top of the Nwell to protect that Nwell region, right. Once this protection is there, now I do not have to bother about another mask in order to have my P-well. I can do a blanket implantation. The P-well and the Nwell are automatically aligned to each other. Okay. This is the interesting point of this. So, then next what do? You do a boron implantation. And you have your P-well. can do a common drive-in step together, so as to obtain your necessary thicknesses of P wells and N wells after removing all this oxide. You have your P well and your N well, and demarcating the two regions you also have a step, right. So, you know the region where you are going to form your N MOSFET and the region where you are going to form your P MOSFET. So, what is going to be the next step? Next step is going to be your active area definition. So, again you form a low cost mask. And then carry out the thick field oxidation. And then remove the low cost mask. Strip off the silicon oxide and nitride. So, you see you have your P well, you have your N well, you have certain regions protected by the thick field oxide, and this rest of the portions are for your active transistors. So, this is a true Twinwell technology, a true Twinwell technology. You have formed really both a P well and an N well. Okay? As the CMOS becomes more and more complex, we have to add other process steps in addition to these basic steps. See, so far whatever CMOS technology we have discussed, no, we are only using a bulk substrate layer, right. We do not have to use, so far we did not have to use a buried layer or an epitaxial layer, so far we did not use that. So far we only have P well and or N well, right. If you are having a Twinwell technology, you have both an N well and a P well, otherwise you have one or the other. Now, CMOS devices, however, can have a very serious problem called the latch-up. Latch up in CMOS devices. Okay. Now, you see a CMOS inverter, a basic CMOS inverter is something like this. You have this is your input, this is the output. Okay. This is grounded, this is VDD. This is the basic CMOS inverter. The top one is the P channel device, the bottom one is the N channel device. You use the P channel device as the load, the N channel device as the driver. Right. So, this is your basic CMOS inverter. Very simple. If your input is high, okay, this gate has a high voltage, it is an NMOS. So, it is going to conduct, okay. We have a path for the current, therefore, the output is going to be low. Inverter. If the input is low, this gate is not going to conduct, the output is going to be high. Right? Now, if a CMOS inverter is connected like this in a transistor, in a circuit. If I have a CMOS inverter like this, what do I have? I have a let us say this is my Nwell. So, this is my PMOS, P plus, P plus, this is N plus, N plus, two gates are tied together, right. These two are also tied together. This N plus is grounded. Usually have a P plus here, this is a substrate contact which is also tied up to this. Now, you see, if because of the presence of a noise signal, this V output goes below the ground potential. Suppose because of the presence of a noise at the output terminal, you have a negative voltage spike appearing, so that this PN junction gets forward biased. You see, this P is tied to this, it is grounded. So, this P is at ground potential. At this N, if you have momentarily a negative voltage appearing, then this PN junction is going to get forward biased. So, what will happen? This N plus region will inject electrons here. Okay. Now, you see, in this particular structure, I have two transistors as well, N, P, N, right. This N plus, this P type substrate and this Nwell, there is an NPN transistor. Similarly, this P plus, this Nwell and this P type substrate, I have a PNP transistor also. I have both an NPN transistor and a PNP transistor. Okay. Now, what will happen? These electrons can enter this NPN transistor, you are injecting electrons here, it can go out in this. So, what is basically happening? It is an NPN transistor, you have forward bias the base emitter junction, right. So, it starts conducting. Okay. And so, these electrons are finally collected out here. This is the substrate contact for this Nwell. So, they are finally collected out of this, go out in through VDD. If there is sufficient resistance in this Nwell, remember your well doping concentration is pretty low. If there is sufficient resistance here, there could be a potential drop as the current is flowing, right. There could be a potential drop, and it could so happen that this potential drop is sufficient to turn on this PN junction as well. Okay. So, the process will be regenerative. Essentially what do you have is called a NPNP structure, right. You know that thyristor is an NPNP or PNPN structure, right. Now, the problem in this is that once the noise spike has occurred, which is sufficient to turn on this junction, and there is flow of electrons, and in that process there is a sufficient potential drop. So, that this junction again gets forward biased and keeps injecting holes here. The process just goes on and on. It becomes a regenerative process. So, even after this noise signal, even if this noise signal is momentary and even if it is withdrawn afterwards, right, it does not stop, the process just continues, right. So, this is called the latch-up. This is called latch-up. This is because every CMOS device, if you have a CMOS inverter, because of the way it is connected, you always have a NP-NP or PN-PN combination, which is a potentially dangerous combination. Once it gets fired, you know, once the thyristor gets fired, you do not have a control on it except by switching off, right. So, once this NP-NP structure fires itself, even after the noise signal is removed, you can't really control it. So, the latch up is actually a major problem in CMOS. One way you can prevent this latch up is, you see, essentially we have two transistors NPN and PNP, by keeping the beta of these transistors low. Okay. And one way, this is the older technique of keeping the beta of the transistor low, that was by doing gold doping or neutron irradiation, so that the lifetime is killed. But these techniques are not really used very much these days, because you can't accurately control. So, that technique of controlling beta is not very much in use. The other option is, of course, you understand that all this is happening because of the substrate resistance, right. The whole point of the regenerative mechanism, suppose electrons are injected from here, fine, they are collected out of this VDD. If the matter would have stopped there, fine. But what is happening? In the process, we have a sufficient resistance drop here, so that you know this is actually connected to VDD. Okay. This point between this and this, you have a sufficient voltage drop, so that this Nwell is actually at a lower potential. That is what is making this PN forward biased. That is what is causing the regeneration problem, regenerative problem. So, the other possibility is you try to keep the well resistance low. You do not allow a sufficient resistance to be there in order that this regenerative mechanism can take place. But that has its drawback. How can I control the well doping concentration? How can I allow the well doping concentration to go high? If the well doping concentration is high, then the device is more prone to the body effect as well as to the capacitance effects. So, we cannot just like that allow the well doping concentration to go high. What then can we do? We can have buried layer, we can have an epi material, you can have this Nwell as a you can have the substrate material itself as P on P plus type. Okay? Or what you can do is you can use what is called the retrograde structure. And what is a retrograde structure? In a retrograde structure you have buried layers, that is if I can have an N plus region here, then the current will always flow through this, right. But as far as the depletion layer is concerned, you still see the low doping concentration of the Nwell. I am cutting down the shunt resistance path without actually affecting the doping concentration of the well. So, this is called the retrograde structure, and the retrograde structure has now become quite popular in CMOS, in which case what we do is aligned with each well, P well and N well, we have a P plus or an N plus buried layers. Buried N plus layer with the N well, buried P plus layer with the P well, which actually brings the CMOS technology quite close to the bipolar junction transistors, because now you need to have the buried layers, right. So, you see one possibility will be to use steps analogous to the bipolar junction transistor. You just have a buried N plus as well as a buried P plus, and then on top of that you grow an epitaxial region, and then you just create your wells in that epitaxial region. Make sure that the epitaxial region is aligned to each other. I mean the well is aligned to the buried layers. So, this is one way in which CMOS technology is coming close to bipolar junction transistor technology, and which is in fact utilized when one is making the bi-CMOS devices. So, we will talk about the retrograde wells with epitaxy for CMOS in the next class, and then we will see how from there we can realize a bipolar junction transistor in the same process flow.